when we take a look at delta M mix, for emphasis, it's basically just taking the difference between your actual M property and the ideal solution version of that M property. And so that means that we also said that delta M mix was just equal to this. I equals 1 C Ni Mi, some temperature and pressure. Okay. And so this term is the ideal solution prediction, and this term would therefore be your actual value. And so based on this relationship, we could then move forward and just say that your actual value, MTP, and also a function of the moles in the system, that's just going to be equal to the summation of Ni partial molar Mi at some temperature and pressure. Right? So this is the effective molar quantity of a species once it's added to a mixture. And so this is going to be a fairly important relationship for us. And what we want to do is at least go through the logic of this relationship. And so we're going to do a quick proof of this relationship. Okay. So we want to show why this relationship is true. Okay. All right, and so for our proof, what we're going to do is we're going to consider a mixture made up of C number of chemicals, or C components. Okay? Where the total moles in the system, which for shorthand I'm just going to call N, that's equal to the sum of all of our Ni's. And that our total extensive property M of the mixture is going to be a function of things like temperature, pressure, and then every single one of the moles of the different species. And so here, take notice that it's not C minus 1 species anymore. It's all the species, because now I'm not dealing with mole fractions. I'm dealing with just the molar values. Okay, in any case, if we take the total derivative of M, it follows this format. P and all of our Ni's, dt, plus dm, dp, t, ni, dp. And then we're essentially also going to take the partial derivative of M with respect to every single one of these different chemical species. Okay? And as we've seen before, the partial derivative of M with respect to the moles Ni, that's just the definition of the partial molar quantity. And so this third term is actually going to be a summation of all the partial molar quantities, and then dni here. Okay? Alright, and so that's just the total derivative of M, so that's just pure math right there. The other thing I want to say is our M here, we could also write that in terms of the molar M, where if we take molar M and multiply by the total number of moles in the system, we get back M. Okay? Alright, I'm going to call this equation 1. But what I want to do is, since we have this relationship, I actually want to work out the derivative of it. So dn m. And here, what we're going to have to do is we're going to have to apply the product rule. dn. I'm going to call this equation 2. Now the last thing I want to do is now I want to start defining mole fractions. And so we know that the mole fraction of a species I is just Ni divided by the total moles in the system. If we rearrange, we know that Ni is equal to Nxi. Then, because we have this dni up here, we then need to figure out what dni actually is. So if we take the derivative of dni, we essentially need to perform the product rule on this Nxi. Okay? Alright, and so that's a third equation. And what I want to do now is I want to take all three of these equations we sort of derived, and I'm going to combine them. Okay? Alright, and so if we combine those three equations and we go through several steps of algebra, which I'm going to skip, what one can do is you could develop an equation that looks like this. Minus m t xi, so now I'm writing it in terms of mole fractions, dp, minus dm dt p xi dt minus summation I equals 1 c mi dxi close bracket plus open bracket m I equals 1 c xi m I bar close bracket dn is equal to 0. Okay? Alright, and so this is a long equation. Okay? It's a complicated looking equation. But there's one thing that we should think about. So this first term in brackets here, it's multiplied by n. And the second term in brackets here, it's multiplied by dn. And no matter what our values of n or the change in dn are, this equation still has to be equal to 0, right? And so even if we make this number, a billion, and change this number to whatever, this sum is still going to be equal to 0, okay? And so what that means is that in order for this entire equation to be equal to 0, and to be unaffected by whatever our values of n and dn are, what that means is that the stuff inside the brackets has to be equal to 0 at all times. Okay? So let me write that out. Since n is an independent variable, that determines system size, the only way that the above equation is true is if each bracket is equal to 0. Okay? Alright, so that just means that this part has to be equal to 0, and then separately, this part has to be equal to 0. All right. So if we take a look at the right bracket, and we know that that has to be equal to 0, what we could do is we could just rearrange the stuff in the right bracket to get this relationship. Xi I. Or if we multiply both sides by n, we get these relationships. Which, if you already forgot why we did all this stuff, this is what we were trying to prove in the first place. And so by going through this proof, we are able to show that this is true.